So welcome everyone, thanks for coming out. It's good to see you all. And today's topic, of course, is on essential fats. And it's a topic that, number one, is extremely important, and number two, there's an awful lot of confusion about. And we hear all these terms, trans fats, hydrogenated, EFAs, EPA, DHA, GLA, right? And it all starts to sound kind of confusing after a while. So in the next 45 minutes, we're going to try to make sense out of all this stuff so you come out of here with an understanding of how essential fats work and what foods get good fats into us that help our bodies function properly and what fats we could do without that we want to avoid that hurt our health. In terms of how fats help our body function properly, there's so many things that essential fats and fats in general do. They're huge regulators of inflammation. And we all think of inflammation if we sprain our ankle, for example, there's inflammation. But what we find is that when we consume too many unhealthy fats, we are constantly creating low-level inflammation in the body. So for example, when you have inflammation in the arteries, all else being equal, the more inflammation you have in your arteries, the more likely you are to clog them up with fat and cholesterol, and that leads to things like heart attacks, strokes, impotence, claudication, kidney disease, and various other issues. There's also, in recent research, they found that Alzheimer's disease is largely associated with inflammation. So if you can reduce the inflammation through eating different fats in your diet, you can reduce your likelihood of that as well. There's a connection between inflammation and cancer and many other things. So we're going to spend a little bit of time on inflammation to make sure we understand how to keep our inflammation under control by eating the right kind of fats. After that, we're going to talk about how the fats that we eat incorporate into the membranes around our cells. Every cell has a membrane around it, and those membranes are made largely out of fat. When we have the right mix of fatty acids in the cell membranes, then various hormone receptors that are embedded within those cell membranes work properly. When we have the wrong mix of fats, those hormone receptors don't work right. And the bottom line, as we'll discuss later on, is that we end up with high blood pressure, depression, diabetes, and other various complications that we can do without, that we can change, not needing medication, just by changing the fats in our diets. So given that, are we all ready to learn a few things about fatty acids and essential fats? All right, very good. Now that we know a little bit about how important things are, we're going to take a look at the basic structure of a fat. And if any of you remember back from high school chemistry, or maybe even if you're a science fiction buff, they talk about how the basic physical foundation of life on the planet is based out of carbon. Anyone ever hear that? Or remember in science fiction movies, I remember one time some alien lady was referring to the human beings as the carbon units. So, like we are carbon units, quite literally. Oh boy, that pen is not in good shape. So we're going to have to go with the unicolor here. So fat, just like us, starts out with a chain of carbons. And this dash in between the carbon here represents an electron that those carbons share together, and it makes the carbons stay together. Based on the nature of carbon, it has 4 extra electrons, and this is about as technical as it's going to get, so don't worry too much here. Carbon has 4 extra electrons that it can share with a neighbor. And when it's sharing all 4 of those electrons, then it's happy. So molecules tend to form that way because carbon has a tendency to do that. And that's why it can create different structures. So something called hydrogen comes along, and what hydrogen is it's just simply a positive charge all by itself. It sees carbon's extra electron to share with, and it says, hey, I'm a positive charge, an electron's a negative charge. If I get together and have a proton and an electron, I'm going to have a balanced equation and be happy. So we're going to add a few hydrogens along here. And for those of you who want to know the technical details, we have a little bit different thing at this end. This is actually called the acid group, and these carbons and hydrogens are called the fat group. So it's a fatty acid. Now hydrogens, like we said, have a positive charge. And have you ever taken 2 magnets that have the same charge or the same polarity and you try to push them together? What happens? Do they stick Or do they sort of repel each other? They repel each other. So what happens is this hydrogen, if it's getting repelled by this one and heading over this way, well, it can't go too far because it's got another one on the other side to push it back. And that repelling energy around the top and the bottom of the carbon chain keeps those hydrogens locked in place, and it actually keeps this molecule straight and stiff and rigid. So let's take a look at another fat now. We're going to start out with our same carbon chain, and we're going to add a few hydrogens here. Let's draw a line there so we don't get those confused. And we'll draw our little acid group at this end. That's an H. And we're going to leave these alone for a minute. Now, let's just imagine that these two carbons have been hanging out in the same carbon chain for quite some time. They're neighbors, and they've gotten to know each other. In fact, they really develop a really strong connection. And they say, you know what? It's really nice that we're next to each other and we share this electron with what's called a single bond. But you know, we like each other so much, we'd like to have what they call a double bond or a stronger connection. So what we're going to do is we're going to share two electrons together. And that's going to create, let's put it right in here, that's going to create what they call a double bond. So now things change. Remember we said that carbon has 4 extra electrons that it can share with other atoms to make up different molecules. Well, let's take a look at this carbon now. It shares 1 electron with its neighbor to the left. Now it shares 2 electrons with its neighbor to the right, so 3 out of 4 of the electrons are accounted for. So it doesn't need a hydrogen on the top and the bottom anymore. There's only one more space. So we're going to put a hydrogen up on the top, and we're going to leave an empty space on the bottom. Same with this one. 1 electron here, 2 electrons here. We're only going to need to add 1 more hydrogen, and we're going to put it up top. So based on what we talked about before, that these hydrogens are all repelling each other on the top and pushing away from each other, and they're doing the same thing on the bottom, but now we have this empty space, is this molecule going to be straight and stiff and rigid like the top one, or is it going to do something different? And what would you say, ma'am, it's going to do? Well, you have no idea, but it's going to do something different because we have a different configuration. It's probably going to, exactly right, good. So it's going to do something like this, right? It's going to flex down because these hydrogens are pushing away, and you have 4 on the top and you only have 2 on the bottom to push back. So it's going to flex down. And when we have a double bond here, and then less hydrogens, that changes everything. Now what happens is this fat on the top, we could say that the carbon chain is saturated with hydrogens. So it's called a saturated fat. This one here is not saturated with carbon, so we call that an unsaturated fat. And we've all heard, for example, that saturated fats are solid at room temperature, and unsaturated fats are liquid at room temperature. So to use a non-vegetarian analogy, I remember back when I was a kid, my mom would make some turkey soup after Thanksgiving. And if the big bowl of turkey soup was on the counter, out at room temperature, the fat layer would come to the top and it would be pretty solid. But if you had a bottle of olive oil next to the turkey, that olive oil would be liquid at room temperature, right? So the olive oil looks like this. It's an unsaturated fat, and it's curved, whereas the turkey fat is more saturated, and that's why it's solid. It's sort of the analogy that if you took a newspaper and it was all put together like you normally get a newspaper, it's fairly dense and everything's lined up. But if you took some of the pages out individually and crumpled them up, right, made them curved and a different shape, you couldn't pack them together as tightly anymore, so that the crumpled up paper would be looser and lighter than the newspaper where the sheets are all lined up together. Does that make sense so far? And the more double bonds you put in a fat, the more it curves. And based on the different structures of different fats, they act differently and do different things in the body. Just like a spoon and a fork have similar structures but a little bit different, and it would be pretty hard to eat soup with a fork, and it wouldn't be so easy to have your salad with a spoon. You could kind of do it, but just that little bit of change makes a big difference. Now, most fats are 18 to 22 carbons long. And we're going to take a look at one here. Oh, and by the way, we've all heard the terms omega-3 and omega-6. Does anyone know how they get those terms, like what omega-3 actually means? Does anyone feel brave? All right, well, what it means is it's really very simple. It means that if you have an unsaturated fat, and you start from the left end, just like we read words, the letters and words from left to right, well, we read fatty acids the same way. And let's look at where this double bond is. We've got 1 carbon, 2 carbon, 3 carbons. After the 3rd carbon is the double bond. So this fat, for example, would be considered an omega-3 fat. Just means the first double bond is after the 3rd carbon. And there's a whole family of omega-3 fats, as we're going to take a look at here in just a moment. If this was a longer chain and the first double bond was after the 6th carbon, that's an omega-6 fat. Does that make sense? Now, so let's come on over here now, and let's take a look at our omega-3 family. And there's really 6 of them, but we're going to look at the number 1, the number 4, and the number 6 fat, because those are the things that are most relevant for this discussion. Our body is not capable of inserting double bonds to the left of the 7th carbon. So therefore, if the body can't make this stuff, an omega-3 or an omega-6, it just doesn't have the enzyme capability of doing that, that means there's 1 omega-3 fat and 1 omega-6 fat that are called essential fatty acids. And an essential nutrient means that your body doesn't make them and you have to get them from the outside. So the omega-3 essential fat is called alpha-linolenic acid. It has 18 carbon chain, it has 3 double bonds, and it's an omega-3 fat. Now what happens is enzyme systems come along and they add some double bonds, or they add a couple of extra carbons, and as we go along, we get longer chain fats with more double bonds that are more unsaturated, that now have a different structure than the previous fats. So we get to one here called EPA, and it has 20 carbons and 5 double bonds, and it's still in the omega-3 family. Now EPA is very important because it helps, as we'll see more in the next picture here, it helps control or reduce inflammation. And that's really good because most of us have too much inflammation and it causes the problems we mentioned earlier. A couple more changes happen, and then it turns into something called DHA, docosahexaenoic acid. And a hexagon has 6 sides, DHA has 6 double bonds. EPA stands for eicoso, which means 20 in Greek, eicosapentaenoic acid. And we know the pentagon has 5 sides, so EPA has 5 double bonds. DHA is extremely important for brain function as well as hormone regulation, as we're going to learn in a couple of minutes. So let's take a look now at the inflammation pathways here. So here's alpha-linolenic acid, EPA, and DHA, just like we just saw. Now there's an omega-6 fatty acid as well, and that one's called linoleic acid. It has its first double bond after that 6th carbon, and the body can't put that there, so we have to get it from the outside. That does the same kind of thing. Enzymes come along and add some double bonds and add some carbons and change things, and what happens is linoleic acid gets converted to something called DGLA, or dihomo-gamma-linolenic acid, for those of you who want to know the term. That also helps reduce inflammation. But then it immediately gets turned into this thing called arachidonic acid, and arachidonic acid promotes inflammation. And what happens is this stuff, linoleic acid, is found in things like corn oil, cottonseed oil, sunflower, and safflower oil. And if you look at most prepared processed foods that aren't so healthy, you'll see usually significant quantities of these oils. And we're getting too many omega-6 fats, which means with too much of this, we end up with too much arachidonic acid, and we're promoting inflammation in the body, and that's leading to various disease processes. Now, arachidonic acid and DHA are both extremely important fats to become part of the cell membranes. Remember we said the membrane, there's a membrane around every cell in your body, and that's what divides the outside from the inside. So you could say that these doors and the wall and the windows here is the room membrane. It divides the inside of the room from the outside of the room. And again, the membrane is made largely of different fats. So let's just say you sprain your ankle. You're going along and you damage your ankle and you tear up the cells that make up the cartilage and the tendons and the ligaments. And what happens is the contents of those cells, including the contents of the cell membrane, spills out into the extracellular fluid. Well, now that arachidonic acid has come out of the cell membrane and it's out there in the fluid, it starts to promote inflammation. Now, of course, not all inflammation is bad, because that swelling that it causes lets white blood cells come in there and it helps the body heal itself. But imagine if you were spraining your ankle all the time and causing constant inflammation, that would be too much and it wouldn't be so good. So just like we have arachidonic acid in our cells, animals have arachidonic acid in their cells. So when we eat animal products, and also when we eat dairy products, we are eating arachidonic acid directly, and that's contributing to the underlying low-level inflammatory, unhealthy state that most people are chronically in, which leads to, it's a big contributor to why we're as unhealthy as we are. Now, we mentioned that our cell membranes contain arachidonic acid and DHA. So especially when a young child or an infant or a fetus is developing, the mother has to supply a lot of arachidonic acid and a lot of DHA, because the cells are dividing, the baby's growing, and it needs those raw materials. So therefore, mother's milk, as well as dairy products, can also contain arachidonic acid. So from the animals themselves and the dairy products, we're getting too much arachidonic acid, and we're creating inflammation. When we eat processed junk food, like unfortunately some of the foods here, even though they may be vegetarian or vegan, are full of these unhealthy omega-6 oils, this stuff gets converted to arachidonic acid, and we're also promoting inflammation. Now, what counteracts that is this guy here called EPA. EPA helps reduce inflammation. And when we have the right balance of arachidonic acid and EPA, inflammation stays in check. Well, where do we get EPA from? Well, we can get it from cold water fish. But if you want to take the vegan approach, you don't necessarily have to do that. You can consume the omega-3 essential fat in the form of alpha-linolenic acid. So where do we get this stuff from? Who wants to say? Where do we get alpha-linolenic acid from? Flax seeds. I heard flax seeds. Hemp seeds. Very good. Any place else? Leafy greens. Who said that? Good answer. All right, we got an advanced group here. And where else? Walnuts. Walnuts are pretty good. All right, so you guys are pretty well educated. We need approximately 2 grams of alpha-linolenic acid per day, as long as everything else is working right, in order to maintain the proper inflammation and to stay healthy. Now, this gentleman mentioned leafy greens. So it's interesting that alpha-linolenic acid, because of its structure, because of the way it's formed, and also because it has 3 double bonds in it, and every time there's a double bond, we have not 1 electron shared, but 2 electrons shared. Every time there's a double bond, that extra electron can actually conduct electrical impulses and help various things perform like they're supposed to. So alpha-linolenic acid is in green leafy vegetables because it helps the plant convert sunlight into carbohydrates, proteins, and fats. So if you were to eat about 125 calories, let's say of lettuce or some other leafy green vegetable. Now, admittedly, that's a fair amount. If you look at lettuce, that's 2 decent-sized heads of lettuce. But just for illustration purposes, if you ate 125 calories worth of lettuce, you would get 1 gram of alpha-linolenic acid, or half your day's supply just from the lettuce. And I'm going to hold off on questions till the end if you don't mind, but you can be first as soon as we're done at the end. Now, if we also look at regular fruits and vegetables, has anyone ever heard that grapes or bananas have alpha-linolenic acid or omega-3s in them? Well, you probably maybe have heard that, but they do actually. Now, not in large quantities, but if you eat enough of those, you do get enough. So if you ate, for example, 1,000 calories, and let's just say that would be about half of your diet. If you need 2,000 calories a day, which is pretty typical, if you ate half of your calories, or 1,000 calories from just non-leafy green fruits and vegetables, that would supply 1 more gram of alpha-linolenic acid. So imagine that you eat a lot of raw fruits and vegetables, including some leafy greens. You could technically get your 2 grams of alpha-linolenic acid just from that. Someone else mentioned flax seeds. 1 heaping tablespoon of flax seeds contains 2 grams of alpha-linolenic acid. So just from, not a level one, but a heaping tablespoon gives you all your omega-3s that you need for the day. Now, flax, the fat in flax seeds is about 58% alpha-linolenic acid. So there's more omega-3 fats than there are omega-6 fats. Now, hemp seeds are also good sources of omega-3s, but there's about 3 times more omega-6 than there is omega-3. That's not necessarily a problem, but we're going to talk a little bit more in just a minute about the ratio between omega-3s to omega-6s. Walnuts are also a pretty good source, but the ideal ratio of omega-6 to omega-3 is probably somewhere in the range of about 4 to 1, somewhere between 4 to 1 and 1 to 1. If we look at traditional human diets where they were tended to be healthy, that's about what we'd see. Now, walnuts have a 7 to 1 ratio of omega-6 to omega-3. Now, the average American, because they're eating all this processed stuff, and because they're eating a lot of animal products, they have about a 20 to 1 ratio of omega-6s to omega-3s. So you can imagine then you're not getting enough of this that reduces inflammation, you're getting a lot of this that promotes inflammation. That's a problem.